In our last module, we have discussed sequence of functions, their convergence, namely pointwise convergence and uniform convergence, and discussed some tests or some methods to find pointwise convergence and uniform convergence. So, we have given examples on pointwise convergence and uniform convergences over some series, over some sets of X. In this module, we shall discuss some consequences of uniform convergence. Actually, uniform convergence enables us to interchange a number of mathematical operations. For example, we can interchange the operations of limit, one limit on x and another limit operating on n. We can exchange these two types of limits when a function is uniformly convergent, and this can also be seen that we can have some similar result when we integrate or differentiate a uniformly convergent sequence of functions. So, in addition, we shall also discuss series of functions, that is just extension of sequence of functions to some summation. We shall discuss also their convergence, some sufficient condition which is known as Weierstrass M test, and then conclude. In our last module, we have discussed pointwise convergence and methods of checking pointwise convergence, and also discussed uniform convergence together with some examples. In this module, we start with some consequences of uniform convergence. Actually, uniform convergence enables us to interchange some mathematical operations, where the mathematical operations involve limits, differentiation and integration. So, we start with some consequences of uniform convergence. So, first of all, we discuss uniform convergence and limit interchangeability. Actually, a sequence of function f n x is a function of both n and x. So, we can take limits either on n or on x. So, if f n x is a uniformly convergent function, then the limits on x and limits of n are interchangeable. So, formally, if f n x converges pointwise to f x on a, where f n is continuous on a for every n, then f is also continuous on a, and then for every a belonging to a, we have limit as x tends to a of limit n tends to infinity f n x is the same thing as limit n tends to infinity of limit x tends to a f n x. So, the implication of the above is that if the limits are not interchangeable, the uniform convergence does not hold. So, this result gives us a condition of checking uniform convergence in some indirect way. For example, consider f n x as x to the power n, x ranging from 0 to 1, where the 0 point is included. Then the pointwise limit of the function of the sequence of function is simply f x, which is 0 for every x belonging to 0 1. However, limit of f n x equal to 1 when x equal to 1. Thus, as x tends to 1, the limiting value of f x is not the same as the double limit of f n x. Hence, the convergence cannot be uniform over the whole 0 to 1 interval, the closed interval. Next, consider uniform convergence and differentiation. If f(n)x is a sequence of functions on AB, closed interval AB, such that for some x naught belonging to open interval AB, f(n)x naught tends to f(x naught), and fn dash x, that is the first derivative of f(n)x with respect to x, exists at all x belonging to closed interval AB and converges uniformly to some function g on closed interval AB, then fn(x) converges uniformly to fx on closed interval AB and gx equal to f dash x for all x belonging to closed interval AB. That is, precisely we have the following result, that is limit n tends to infinity of the first derivative of fn(x) is the same as the first derivative of the limit function of fn(x), and this holds for every x belonging to the closed interval AB. So, let us consider some example. Consider fn(x) a sequence of function on the closed interval -1 to +1 defined by x divided by 1 plus n square x square. Now, define fx as 0 for all x, and then it can be shown that mn, which is nothing but the supremum value of the absolute value of fn(x) minus fx over the range over the closed interval -1 plus 1, which is 1 by twice n, and this tends to 0 as n tends to infinity. Thus, the convergence is uniform. However, if we calculate the first derivative with respect to x, we get the expression 1 minus n square x square divided by 1 plus n square x square whole square, and hence for x equal to 0, we get the limit of the first derivative as 1. Hence, limit of the first derivative is not equal to the derivative of the limit function, at least for x equal to 0. Next, consider consequence of uniform convergence and Riemann integrability. Suppose fn(x) is a sequence of Riemann integrable functions on closed interval AB such that fn(x) converges uniformly to fx on the closed interval AB, then f is also Riemann integrable on the same interval, and the limit of the integral of fn(x) is the same as the integral of the limit of fn(x). That is, in this case, uniform convergence enables us to interchange the operations of integration and limit. So, for example, consider fn(x), which is defined as nx e to the power minus nx square for x belonging to closed interval 0 1. Now, in this case, it is already shown that fx comes out as 0, and we can show that mn, which is the supremum value of the absolute value of fn(x) minus fx over the range 0 1, comes out as square root of n by 2, which tends to infinity as n tends to infinity. Therefore, mn does not tend to 0, and hence the convergence is not uniform. Now, as a consequence, we find that the integral of fn(x) over 0 to 1 comes out as 1 minus e to the power minus n divided by 2, which goes to half as n tends to infinity, but integral 0 to 1 fx dx, that is the integral of the limit function, comes out as 0. So, these two are different. However, if we consider the interval 1 to 3, the closed interval with endpoints 1 and 3, then mn as defined earlier comes out as n multiplied by e to the power minus n, which tends to 0, and hence the convergence is uniform over the closed interval 1 to 3. Therefore, it can be seen that the operations of limit and integration are exchangeable. So, we get in both cases the same value. So, let us pass to our next topic, which is a series of functions. We have already discussed a sequence of functions and their convergence. So, like ordinary series, the idea of sequence of functions can also be extended to series of functions. For example, we have well known E series and log series. As earlier, we can have different concepts of convergence, that is, we have either pointwise convergence or uniform convergence, and however, the series is defined in the same way as we have defined series for the ordinary sequence. So, let f(n)x be a sequence of functions on A to R, then the sum f1 plus f2 plus f3 up to infinity is known to be a series or infinite series and is often denoted by summation n from 1 to infinity f(n)x. Define the sequence of partial sums of the infinite series by Sn(x), which is defined as summation k from 1 to n fkx. If the sequence Sn(x) converges pointwise to some function Sx on A, the series summation fn(x) is said to converge pointwise to Sx on A. However, if the convergence is uniform to some Sx on A, the series converges uniformly to Sx on A. In addition, if the series with the absolute values of fn(x) converges for each x belonging to A, the original series, that is the series with fn(x), is said to converge absolutely on A. So, let us consider some examples. So, first consider the series defined by x square plus x square by 1 plus x square plus x square by 1 plus x square whole square for x belonging to closed interval 0 1. Then in this case Sn(x) comes out as 1 plus x square minus 1 plus x square whole to the power minus n plus 1, and this is our nth partial sum. Thus, we find that limit of Sn(x) is 0 for x equal to 0, and it is 1 plus x square if x belonging to the interval 0 1, where the endpoint 0 is excluded from the interval. Thus, Sn(x) converges pointwise to Sx, which is defined as 1 plus x square multiplied by the indicator 0 less than x less than equal to 1. Hence, the series converges pointwise to Sx on closed interval 0 1. However, Sx is not continuous on the closed interval, but each Sn(x) is continuous on closed interval 0 1, and hence as we have seen from the consequences of uniform convergence, that here the convergence is not uniform over the unit interval 0 to 1. Consider our next example, which involves the nth term x to the power n multiplied by 1 minus x to the power n for x belonging to closed interval 0 to 1. Then in this case we get a geometric series, and so Sn(x) comes out as x into 1 minus x multiplied by 1 minus x into 1 minus x to the power n minus 1, whole thing divided by 1 minus x multiplied by 1 minus x. Thus, it is easy to observe that the limit function of Sn(x) comes out as 0 if x equal to 0 or 1, and it is x multiplied by 1 minus x, whole thing divided by 1 minus x multiplied by 1 minus x if x belonging to the open interval 0 1. Thus, Sn(x) converges pointwise to Sx, and hence the series converges pointwise to Sx on closed interval 0 1. Next, consider the series with the nth term as sine of nx whole thing divided by n to the power p, where x belongs to the real line. So, let us fix x at some point a and consider the convergence of summation sine of na divided by n to the power p. Now, we know that since sine functions are uniformly bounded by unity, the absolute value of sine na divided by n to the power p less than equal to 1 by n to the power p for every n greater than equal to 1. Hence, by comparison test, the series with a converges for p greater than 1, that is, the series converges absolutely. Since a is arbitrary, the original series, that is summation sine nx by n to the power p, is absolutely convergent on R for p greater than 1. However, for uniform convergence we need some simpler conditions or tests like ordinary series. Otherwise, this problem of checking uniform convergence cannot be tackled. So, we have one such test. Actually, there are a number of tests, but we are just discussing the most useful test and the most simple test. So, this test is known as Weierstrass M test. Let fnx be a sequence of functions on A such that for every n greater than equal to 1, absolute value of fnx less than equal to mn for any x belonging to A, where mn is naturally independent of any x and depends on n. Then the series summation n fnx converges absolutely and uniformly if the series summation mn is convergent. So, we have just one observation: the above test only provides a sufficient condition, and hence it may be possible that summation fnx converges uniformly, but summation mn diverges for best possible choices of mn. So, actually our best possible choice for mn can be used as mn as the supremum value of absolute value of fnx, where the supremum is taken over some set A. So, let us consider some example. First, consider the series with nth term cos nx by n to the power p. It is well known that cosine functions are uniformly bounded by unity. Therefore, absolute value of cos nx divided by n to the power p less than equal to 1 by n to the power p for every n greater than equal to 1. Thus, we define mn as 1 by n to the power p. Since the series summation mn converges for p greater than 1, which follows from the convergence of p series, the given series converges absolutely and uniformly on every x belonging to the real line. Consider our next example, which has the nth term as x square divided by 1 plus n square x square. Now, x square divided by 1 plus n square x square can be written as n square x square divided by 1 plus n square x square whole thing multiplied by n to the power minus 2. Since this n square x square divided by 1 plus n square x square is bounded by unity, we get that x square divided by 1 plus n square x square is less than 1 by n square for all x belonging to the real line. This suggests to take our mn as 1 by n square. Since the series summation mn converges, the given series converges absolutely and uniformly on x belonging to the real line. Consider our next example. Suppose we have a series summation n from 1 to infinity x divided by n plus n square x square for x belonging to real line. Here absolute value of fnx is nothing but absolute value of x divided by n plus n square x square, which is a symmetric function about 0. So, we consider only the nature of this absolute value of fnx for x greater than 0. Now, just a simple algebra shows that the function x by n plus n square x square attains maximum at x equal to 1 by square root of n. So, we can take the maximum value of absolute value of f n x as our mn, and in this case we get mn as 1 by twice n to the power 3 by 2. It is well known that the series with 1 by 2 to the power n to the power 3 by 2 as the nth term converges. So, the given series converges absolutely and uniformly on x belonging to R. Consider our next series where the nth term is x divided by n plus n cube x square. Here x can be positive or negative, but we get the absolute value of f n x as absolute value of x divided by n plus n cube x square, which is again a symmetric function about 0. Now, it is well known from the arithmetic mean greater than equal to geometric mean inequality that n plus n cube x square greater than equal to twice n square absolute value x, which implies absolute value of f n x is less than equal to 1 by 2 n square, and hence using Weierstrass M test taking mn as 1 by 2 n square, we observe that the series converges absolutely and uniformly on x belonging to real line. So, next we shall discuss uniform convergence of a series of functions and continuity, the role of continuity. Consider a series of functions summation f n x. Suppose f n x is continuous on A for every n greater than or equal to 1, and summation f n x converges converges uniformly to f x on A, then f x is also continuous on A. So, continuity of the limit function is just a consequence of uniform convergence of the series. In our next result, we shall discuss interchangeability of differentiation and limit. Consider a series of functions f n x for x belonging to the closed interval a b such that the series with nth term f n x naught converges to f x naught for some x naught belonging to a, that is here a is nothing but the closed interval a b. F n dash x exists at all x belonging to a b, and the series with f n dash x as the nth term converges uniformly on the closed interval a b. Then the differentiation can be made under the sign of summation. So, lastly we just discuss interchangeability of integration and limit. Consider a series of functions f n x, x belonging to the closed interval a b such that each f n x is Riemann integrable on the same interval, and the series with nth term f n x converges uniformly on the same interval. Then summation over the integral of f n x is the same as the integral over the summation of f n x. So, in this case we find that uniform convergence enables us to interchange the integration and summation operations. So, we have seen the consequences of uniform convergence in terms of interchangeability of some mathematical operations like limit, differentiation and integration. We have also seen series of functions and discussed their convergence. So, in our next module we shall discuss one particular series which is commonly known as power series, and this is the most important quantity or the most important thing in statistical literature. For example, we can have power series distributions, we can have exponential distributions, we can have Poisson distributions, which are nothing but some power series.